the lecture of today will be about the sum of independent random variables. In the last lecture, we saw that if you have, if x and y are two independent random variables, and x is with the density fx of x, y is with density fy of y, and then you consider the random variable z is equal to x plus y, and you want to know what is the density of z, then what happens is that f z of z is equal to the integral minus infinity to plus infinity of, you can write it this way, it's fx of x times fy of z minus x dx. And this is called the convolution integral. It turns out that you can make a change of variables, and you can also write this as this is equal to the integral minus infinity plus infinity of fx of z minus y, fy of y, dy. So it's the same. Basically, the change of variable in this case, when you go from here to here, is that you call this object y, and that's the change of variables. So that's the same, which means you can decide which of the two you leave unchanged, and the other one will be z minus the other. Then as an application of this, what we have seen is that if you take the first application we considered was the case in which x and y are uniformly distributed. So x and y are both uniform, 0, 1. And then the result was that the f z, if you remember, it's a function. Instead of rather than writing the expression, I just show the picture. It's this function here. It's 0, 1, 2. This is 1. Right? We show this, and then now if you consider three variables, so if you set, for example, now what is the generalization? If you take z to be equal x1 plus x2 plus x3, if you assume that x1, x2, and x3 are uniformly distributed, then you will obtain another function. First of all, if x1, x2, and x3 are uniform 0, 1, then the support of the density, this will go from 0 to 1. So the support, which is the set of the interval in which these functions are non-zero, will be from 0 to 3. So and then you can show that the function is like this. In particular, this piece here, in this 0, 1, the function will be x, this is x, this is z, and this is f, z, z. And here, this is x squared over, z squared over 2. So in this region here, this is z squared over 2. Because that's more or less, if you remember how to construct this, it's you take another triangle, you slide this triangle here, and then you count the area of the overlapping triangles. Now, what is possible to show is that in general, if you take the sum of n of these variables, then the function becomes, well, you see, it's already kind of a bell-shaped. So we already know that, we will formalize this, but as the number increases, the shape will resemble more and more the shape of the Gaussian. And this we will do it later. For the moment, we will be happy to consider this function in 0, 1 and to show that, use this blackboard, to show that f, so suppose that z is a function of n, is a sum. So z is equal to the sum I equal 1 to n of xi, and all these xi are independent random variables which are uniform 0, 1. Now we show that the shape of f z of z in the interval 0, 1, restricted to the interval 0, 1, is equal to x to the n divided by n factorial. And this can be done by induction. On n. We know that this is true for is it n? If it is only 1, is it n? Well, the mistake is that this is not true. This quantity is true. This I don't know. This is certainly proportional to square. I don't know about the normalization factor, but this is what we want to show is this. Capital N. And so, let's assume, so we start from n equal 1. For n equals 1, well, we know that for n is equal 1, in 0, 1, that's f z of z, because z is equal to x1, and x1 is this okay, so it is true for z equal 1. So this is true, so it's true for n is equal 1. Now we want to, given it is true for n is equal, for n minus 1, we want to show it is true for n. So this means that we consider z to be the sum I equals 1 to n minus 1 of x I plus x n. So, we know we have, so for this one, capital F, I think I forgot to mention that there are two ways to write it. This is the formula for the density, but before the formula for the density, in the book we derived also the formula for the distribution function. The distribution function is almost the same. It's just capital F z of little z is equal the integral minus infinity plus infinity of capital F x of x little f y of z minus x dx. Right, so in fact, you first derive this, and then when you differentiate, you derive this. That's what we did the last time. We derived this one, and then you can derive this by differentiation. You remember? That's what we did last time. So now we're going to use this expression here. So you want to compute now fz of little z. What is it? Well, you do the convolution. You do the convolution between, and we choose this expression here for the convolution. You do the convolution minus infinity to plus infinity of capital F Z. How can we call it? We can call this number here Zn to be the sum of n, and this quantity here will be Z n minus 1. So this is the sum of n minus 1 identically distributed uniform distributions, and that Zn is the sum of n. So Fzn is equal to the integral from minus infinity to plus infinity Fzn minus 1 of z minus, we can call it x, doesn't matter, times right? Fine. Now, this is in principle an integral from minus infinity to plus infinity. In practice, this is an integral. You see, this quantity is 0 outside the 0, 1. So in practice, this is an integral from 0 to 1. So we can convert this into an integral from 0 to 1. Fine. And then this, of course, disappears, because in 0, 1, this is 1, outside it is 0. And now, this quantity here is equal to, in 0, 1, we assume Z belongs to 0, 1. Now, x is integrated in 0, 1, z belongs to 0, 1, so what happens? That z, so x, so minus x belongs to minus 1, 0, minus x. And z minus x belongs to z minus 1, z. Is that right? Right? Do you agree? Yes.
Why is z belongs to 0, 1? Are we just doing
Because what we want to prove is that this distribution function of z is equal to z to the n over n factorial only in the first part. Only, you see, when you do this convolution, the shape, the functional form of the convolution changes according to whether you are in the first interval 0, 1, or in the second, or in the third. So the function will be defined like this one. This one is defined, one form in 0, 1, and another form in 1, 2. And the same is true for the distribution function. So there's one expression in 0, 1, another expression in 1, 2, another expression. So we only limit to 0, 1. Otherwise, the expression is very complicated. So I'm saying that if z is if x, so what is it? X belongs to, when you integrate x belongs to 0, 1. So minus x belongs to minus 1, 0. Z minus x belongs to z minus 1 z, right? Now, because z is in 0, 1, z minus 1 is a negative number. And when this quantity f for negative values is equal to 0. I remind you that this quantity f, whatever you do, has the following property. For z less than 0, it is 0. For z less than n, is equal to 1. So this quantity here is 0. Then you have n. So it does something, increases, and here it's 1. So the only thing we want to know is what happens from 0 to 1. But below 0, it's 0. So because this quantity is 0, if z minus 1 is equal to so z minus x belongs to 0 minus 1 z. But when z minus x is less than 0, this quantity is 0. So the only meaningful thing is to integrate when z minus 1, so you want that z minus x, you want it to belong to 0, well, in practice, 0 z. Right? It's only in a subset of this region that you get a non-zero value. If z minus x is less than 0, then this function is 0. So you don't need to integrate when x is from 0 to 1. In practice, it's enough that z minus x belongs to 0 z. So this means when x is equal to z, this quantity is 0. And when x is equal to 0, this quantity is z. So the two extremes of this interval are obtained for x equal z and for x equal 0. So in practice, this interval is equal to the interval from 0 to z of f n minus 1 because if the argument is bigger than z from z to 1, this quantity is 0. This function is 0. So when you integrate this from 0 to z, what you get is up to now you didn't use the inductive hypothesis. Now we use the inductive hypothesis. And now we replace this one by, this is the integral from 0 to z, and this now becomes z minus x to n minus 1 divided by n minus 1 factorial. We are using now here, this is the inductive hypothesis. When you integrate this object, what is this? Well, the primitive of this function, there is a 1 over n minus 1 factorial. Then the primitive of this is z minus x to the n divided by n with a minus sign. And this you want to compute for x that goes from 0 to z. When x becomes z, this quantity is 0. And when x becomes 0, this quantity is z to the n. this is a minus here, but the minus here, so the result is exactly z to the n divided by n factorial. So this is exactly what we wanted to prove. So that's the end of the proof. Okay? So what does it mean? This means the following. For n equal 1, you start like a ramp. For n equal 2, you start like a parabola. For n is equal 3, you start like a cubic. So when n increases, this function will be somehow more and more, closer and closer to 0, start in a smoother and smoother way from 0. We will see that this behavior is common of many sums of random variables. We will see this during this lecture. Okay, that's for the sum of uniformly distributed random variables. Now I can erase and we switch to the next case, the next sum of random variables. Okay, now there is a gamma random variables. I follow the book. Gamma random variables. This gamma function is a little bit hostile, but we will try to make it a little bit friendlier today. So I can erase this. This part is not as it is, it's general. So now we consider the gamma function, gamma distribution. Gamma distribution. So what is the shape that we consider? The shape, I use a notation which is slightly different from the book, because I would like to use the same notation we used before. So before we have I think we can call it T. So we say that T is gamma of parameter alpha if f T of T is equal we call it how do we call it? Well, it depends on two parameters actually. It's alpha and lambda. It's lambda e to the minus lambda t times lambda t to the alpha minus 1. And then we will divide by gamma of alpha. And that's the one that we analyzed before. And then what did we observe? We observed that the first thing to observe is the following. Let's consider alpha equal 1. For alpha equal 1, then this means that ft is equal lambda e to the minus lambda t. This is, there will be no lambda t to anything. And then, okay, it is divided by this gamma of 1. This function is the gamma function, but what is this gamma function? Well, consider the following thing. This is a probability. This is a probability density. So it must be integrated to 1. Indeed, the numerator integrates to 1 already. And so basically this gamma of 1, in this case, gamma 1 is 1, right? So this function is the gamma function. What is the gamma function? Well, Suppose you say, I want to have a probability which is proportional to the quantity that I have in the numerator. And this means that the integral of this object has to be 1. Fine. This means that you remember there is a constant c, and the constant c is the inverse of the integral of the numerator from 0 to plus infinity. In fact, this is for t greater than 0, and that is 0 for t less than 0, right? So this is just a normalization factor. So this gamma is just a normal, you can think as a normalization factor. So the first observation is that first of all, we will see, so this is the exponential distribution of parameter lambda. That's the first observation. The second observation is that, let's see, lambda is a rate, t is a time, lambda times t is a non-dimensional number, so somehow it's a non-dimensional time. For any lambda, we can rescale time and measure time in units of 1 over lambda, and then if you call tau, for example, the quantity lambda t, then you will notice that your f, the new variable, in this parameter, I don't know, how is it Greek? How is it capital tau? No idea how to write capital tau. It's just e to the minus tau. So if you express, so this is e to the minus tau. So if you express in terms of this new time, the rescale time, then this variable f of t of tau will be just e to the minus tau, and this will be tau to the alpha minus 1. It's proportional to this number. It's proportional. And then when this is equal to c times this, and then what is this constant c? When you want this to be 1, so this means that in the denominator, you have the integral from 0 to plus infinity of v to the minus, you can call any letter, xi to the alpha minus 1 big psi. Right? Because this integral is to be 1. And this quantity here happens to be, depends on alpha, so it happens to be the gamma function. It's a function that appears in many contexts. So it is a name. And then what we found about this gamma function, well, we found, well, there are, if gamma is if alpha is an integer, what we found is that the gamma of n is equal to n minus 1 factorial. Well, that's what we already observed. Fine. Then, again, to this quantity here, we want something which is proportional to this. So if alpha is equal to 1, this term does not appear. If alpha is equal to 2, what does it mean? Let's try to draw this family of curves when we change alpha. Let's try to draw them. So, for alpha is equal to 1, we get the exponential. We know that the function is just this. Right? It decays exponentially. For alpha equals 2, what do you get?